Hello everyone, and welcome to this presentation on exoskeleton design using musculoskeletal modeling. My name is Divyaksh S. Chander, and I'm honored to have a chance to give this presentation. I work as a biomechanical specialist at Anybody Technology, and our main product is Anybody Modeling System, which is a software for performing biomechanical analysis. The outline for today's presentation is I'll give a small introduction to Anybody Modeling System, and then I will talk about the application of musculoskeletal models in exoskeleton design with some examples. Finally, conclusion and question and answer at the end. Anybody Modeling System is a specialized software for musculoskeletal analysis that is based on inverse dynamics analysis. As an output from the simulation, we get internal body loads such as muscle forces, joint reaction forces, joint moments, activation patterns, and metabolic energy. The software itself comes with open source body models in the form of Anybody Managed Model Repository, and I will touch upon that in a bit. You can customize your models using your own motion data and then scale the model to your subject and import CAD models to represent the environment more accurately. And then with these outputs, you can export them to finite element software or process them further in your post-processing pipeline, whether it's through Microsoft Office or some other way that you prefer to do. A typical workflow with the inverse dynamics-based simulation is to start with the kinematics analysis. For the kinematics, you need the musculoskeletal model, and then you need to provide some motion data so the body model performs some representative activity. Then you move to the next step, which is inverse dynamics analysis. Here you need to know the external forces that affect the model. These external forces can be measured or they can be predicted by the software, such as the ground reaction force. After the inverse dynamics analysis, you should see some estimates of the internal body loads, such as joint torques, joint reaction forces, muscle activation, and so on. The problem we want to solve today is how to include an exoskeleton model in this analysis. For the kinematics, we need a model of the exoskeleton and some kind of motion data for it. The motion data can be measured if you have a physical prototype, or it can be assumed if you're in the virtual prototyping stage. Then for the inverse dynamics analysis, you want to know the assistive force or torque that the exoskeleton provides, and you also need an interface model that allows a transfer of force between the human and the exoskeleton model. After the inverse dynamics analysis, you should be able to see how the exoskeleton affects the internal body loads, such as changes in muscle activation, joint reaction forces, and so on. And maybe you also get some estimate of the human exoskeleton interface force. The Anybody Managed Model Repository is an open library of models. It contains a detailed representation of the human musculoskeletal structure. It has models of bones, joints, muscles, and ligaments. This detailed dataset comes from several CAD/OS studies done by different research groups. The models have been validated in many studies, and several publications have used these body models. The model can be personalized using easy-to-use anthropometric scaling methods or more detailed methods such as subject-specific morphing with the image data of the patient. Continuing with the topic of motion, I will briefly mention some of the more frequently used systems of motion capture. There are basically two types of files that Anybody modeling system can handle easily. The C3D files, which come from optical marker-based systems, and BVH files, which come from inertial motion unit sensors. There are models available in the AMMR that can use these files directly, and there are other methods that can be used to input the motion into the model, but we will not discuss them today. Talking about forces, there are mainly three types of forces that we are examining in the simulation. There is inertia force. This comes from the mass and inertia property of any rigid body and its movement. Then there is the environment force or the boundary conditions. These are the forces that act on the body from outside, such as the ground reaction force, and these are often recorded in MOGAP systems. Or these could also be the force at the contact point between the human and the environment model. If needed, the software can also estimate these forces. And there are different ways to input these forces, whether they are analytical or synthetic. And finally, the internal body forces. This is an output of the inverse dynamic simulation that tells us what is going on inside the body. Here we are looking at muscle forces and the joint reaction forces. To explain a bit more in detail, in any body modeling system we use the full Cartesian formulation. This means that every rigid segment has 6 degrees of freedom, 3 positions and 3 rotations. And for each of these degrees of freedom, we need constraints in the system. These can be joints between different segments or drivers that specify the motion of 1 or more degrees of freedom. Usually, we can have 2 types of system, the determinate system and the overdeterminate system. The determinate system is where we have all the constraints for each degree of freedom. This means that we can write all the equations and we have the same number of unknowns as the number of equations. And then we can solve this. The overdeterminate system is what we often see when we use motion capture data. So when we have C3D data with many markers on different segments, this means that we have many equations and fewer unknowns, and we have to use the overdeterminate analysis. In this case, we split the constraints into hard constraints and soft constraints. Hard constraints must always be satisfied, while soft constraints can allow some error. And then this problem is solved by an optimization problem which tries to reduce the error in soft constraints while keeping the hard constraints. Next, we will look at the inverse dynamics formulation. So, after we get the motion data and the external forces acting on the human model, we can write all the equations of the motion. Then we have the unknown muscle forces and we have the problem of muscle redundancy. This means that the human body has too many muscles to solve the equations of motion analytically. In anybody, this is solved by direct muscle recruitment. This means that the muscle forces are found by an optimization problem. An objective function is defined. There are different functions that represent different criteria for how the muscles are used. The optimization problem tries to minimize the muscle forces while satisfying the equations of motion and the constraint that muscles can only pull and not push. With this step, we are finding the muscle forces, joint reaction forces, and if needed, the force between the human and the environment in one single step. I will now begin the main topic of the presentation today, which is the use of musculoskeletal models in the design of exoskeletons. When you're considering an exoskeleton, you may have different design questions, such as what human variables are affected, how the load will be redistributed, or how the exoskeleton will affect the metabolic energy. And on the exoskeleton side, maybe you're interested in knowing how much power the actuators need, or how to attach an exoskeleton to the human and measure the impacts of the exoskeleton. A combined human exoskeleton simulation helps answer questions like these. There are many examples in the literature of how musculoskeletal models can be applied in exoskeleton design, and they can be grouped into 3 main stages of the design process. The first stage is the conceptual one, where the goal is to understand the activity that needs assistance and to estimate the internal loads involved. Then, different concepts and methods can be explored to assist this activity, such as assisting different joints. The second stage is the virtual prototyping one, where a detailed digital model is created based on the exoskeleton concept. The final stage is the physical evaluation one, where a physical prototype of the device is built and tested in the lab or in the field, and the effects of the exoskeleton are measured using musculoskeletal models. To go into more detail at the conceptual stage, you want to do the following. First, you want to establish a baseline, which means you want to examine the current situation, the task or activity that needs assistance, and the internal body loads in this task. Then you also want to compare with a reference situation. This helps you set a target for your exoskeleton, and this helps in answering the question, how much should the load be reduced by the exoskeleton compared to the current load? Next, you want to find the best way to provide assistance for your activity. You can do that by applying ideal assistance to different joints and exploring different functions and combinations of assistance and so on. Then Once you have found the best way to assist the activity, you want to create a concept for the exoskeleton design. You want to decide if active or passive assistance is more suitable, what type of actuation to use, whether linear or rotational actuators, and what kind of design specifications to have, such as peak and average power requirement or stiffness constant for passive assistance. One example of this type of study is from one of our previous webcasts, Simulation-Driven Conceptual Design of Exoskeletons. This was by Professor John Rasmussen from Aalborg University, and I suggest you watch this webcast if you have not already done so. The model that I will use as an example is already available in the AMMR, and what Professor Rasmussen explained in this webcast on conceptual exoskeletons is how you can set up a baseline and a target load for the assistive device. In this example of lifting a box, we usually look at the lumbar loads, which are known to be a critical point or stress factor in this activity. We also know the NIOSH recommendations for the lumbar loads, that is the compression force at the lumbar level. And then you may also want to look at some other body loads such as the patellofemoral reaction force. And in this case, Professor Rasmussen suggested that when you do not have a recommendation from some source, then it could be interesting to compare to activities like walking, with the idea that we have evolved over thousands of years and we are very efficient at walking. And this is something we can do several thousand steps every single day without causing any long-term damage to our body. So the logic is that the loads that we see in such an activity must be safe, and that can then be used as a target level or a reference for the patellofemoral reaction force. After defining the target load, you can explore different concepts, and by that I mean looking at idealized assistance, so you don't have to create any detailed CAD models. For example, in this slide there are three cases. On the left, there is no assistance. In the middle, there are rotational springs that help at the knee joint. On the right, there are linear springs that connect the shank and the thorax of the subject. When we check the compression force at the lumbar level, we see that the rotational springs at the knee do not change anything at the lumbar level, but the linear springs reduce the lumbar loads a lot. When we look at the patellofemoral reaction, we see that both rotational springs and the linear springs reduce the first part of the patellofemoral reaction by a lot. So, after that example, I will move on to the virtual prototyping stage. In this stage, you want to create a detailed digital model based on the exoskeleton concept. This lets you make more accurate estimate of mass and inertia properties of the exoskeleton. You can also simulate a detailed mechanism of the exoskeleton and then fit it on to the musculoskeletal model. This way, you can examine issues like kinematic alignment or attachment points between the human and the exoskeleton. Then maybe you can further investigate how the interface shape affects the interaction force or how to optimize the assistive torque by adjusting something in the mechanism. As an example for virtual prototyping, we have a simple model here that I prepared for this presentation. This is a passive shoulder exoskeleton that can assist in overhead tasks. In this example, we have the human model holding a drill machine that weighs 1 kilo. To simplify the model, the task is only to hold the drill. That is, there is no active force on the drill. We recently introduced fatigue models in Anybody modeling system. With the fatigue model, we can simulate a decline in muscle strength over time, and we can use this model to predict real-world performance indicators like endurance time, that is, how long a person can perform a task. This is estimated in the model as the time needed till muscle activity reaches 1 due to the decline in muscle strength. At this point, the person will become too tired to sustain the task conditions. We can see the development of the deltoid muscle activity in the graph, and it hits 1 around 300 seconds or 5 minutes, which I would say is a reasonable value. So In this passive shoulder exoskeleton, the assistance is implemented via an elastic band that connects the attachment point on the arm to a point on the exoskeleton on the back. In this slide, we can study the effects of changing the stiffness constant of the band on the endurance time. Band 0 does not simulate any assistance, and it shows that adding the detailed model of exoskeleton reduces the performance due to the added mass of the exoskeleton. From band 1 to band 4, the stiffness constant is increased and its effect can be seen as an increase in the endurance time. Band 1 is just about sufficient to overcome the presence of the exoskeleton, while bands 2 to 4 show an increase in the endurance time over the baseline. We can also see something really interesting in this table. Normally, in the past, we would look at the muscle activation at the first time step for such static tasks. Now with the fatigue model, we can extrapolate the effect of the change in muscle activation to the change in endurance time. That is, we can evaluate the exoskeleton over a new performance metric. What's interesting about this is that even a somewhat small change in muscle activation can have a significant change in endurance time. For example, for band 3, we see around 10% reduction in initial muscle activation, and this extrapolates to a 22% increase in endurance time. In continuation with this example, we can also simulate the effect of changing the attachment point of the exoskeleton on the arm. In this example, I simulated 3 attachment points: a point close to the shoulder, another point that is close to the elbow, and the midpoint of the upper arm, which is the default configuration. We can see that there are some minor changes in the endurance time due to the change in the attachment point of the exoskeleton. And finally, moving on to the physical evaluation stage. The idea in this stage is that you want to evaluate a physical exoskeleton, which could be in the lab or in the field. You can collect some motion data using C3D systems or BVH-based systems, and you can validate your models using some quantitative measures of the load on the human body, such as the EMG measurements or other types of measures like oxygen consumption or heart rate. These can indicate the stress on the human body. Then with the musculoskeletal model and the other measures that you have, you can document the effects of the exoskeleton and how it affects the internal body loads. You can also make some detailed investigations and try to correlate some subjective and quantitative measures. One example of this type of study is the ANDI project, where an experimental study examined the Pixo shoulder exoskeleton. There were 12 subjects who did 5 trials each, with and without the exoskeleton. Each trial consisted of 24 poses, and the motion was captured with XSense, which is an IMU-based system that produced BVH files. All of this data was processed in Anybody modeling system, resulting in about 3,000 trials. This was a large dataset that enabled individual and grouped analysis of detailed outputs for muscles and joint loads, and it enabled comparisons between with and without exoskeleton cases. Then one can systematically look for advantages or possible side effects from the exoskeleton. In conclusion, musculoskeletal modeling plays a vital role in the design of exoskeletons. The Anybody modeling system offers a comprehensive approach to musculoskeletal analysis, while the Anybody Managed Model repository provides access to a variety of open models for customization. Today, we have seen some case studies illustrating the use of Anybody modeling system in different stages of the exoskeleton design process. If you would like to see some more resources, you're welcome to visit our website www.anybodytech.com, where you can find future events, previous webcast library, publication lists, etc. You're also welcome to visit www.anyscript.org, where you can find several resources on how to use Anybody modeling system. If you have any questions regarding the presentation, please ask during the question and answer session right after the presentation. You're also welcome to write me an email at dsc@anybodytech.com. If you're interested in trying out Anybody modeling system, please write to us at sales@anybodytech.com or contact Gallo System at info@gallosys.com. Gallo System also have a booth at the conference, so it could be interesting to drop by and have a chat with them. With that, I thank you for your attention and look forward to your questions.